So we are on our very last unit in AP Chem, and that is on electrochemistry. So let's start out just doing a little bit of review. This is actually way back from Unit 3. So the very first thing that we want to do is we just want to remind ourselves what oxidation numbers are. If we come down and look at our reaction that's being balanced in acid, remember that if it's a nice monoprotic ion, you're going to go ahead and call the ion charge the oxidation number. They're going to be one and the same. So things like chloride will be -1 and chromium-3 will be +3. If it's an element like this Cl2, you know that all elements, since they have no charge at all, and of course they took no effort to make in the nature, are going to be oxidation numbers of 0. And then remember, there were some very simple basic rules. Take, for instance, oxygen, when it is not its element, is typically a -2. And remember that if that's -2, then we've got 2 chromium atoms, both of which added to our 7 oxygens, each of our oxygens is a -2, have to all add up to be the charge of this ion, and that's a -2. That's going to make each of our chromium ions, doing a little bit of algebra, become a +6. So oxidation numbers, the only rule that we didn't include was, of course, typically hydrogens are going to end up being a +1. So there are your basic rules. Elements, 0. Monatomic ions, the charge of their ion. Oxygen, -2. Hydrogens, +1. And anything else solve algebraically. If you remember, oxidation is the loss of electrons. That means that you are in fact going to see the oxidation number increase. And you can either remember these by thinking about oil rig, which of course would be oxidation is loss and reduction is gain. Or you can use the other one, which is just as good, Leo, meaning a lion, goes grr, and that would be loss of electrons is oxidation, gain of electrons is reduction. Your choice. But we do know that the reduction is going to be a gain of electrons, and since we're gaining negatives, that's going to cause our oxidation number to drop. So as we look down at our example of the dichromate and chloride reaction, we can clearly see that the dichromate is going from a +6 down to a 3. So we can see that the chromium is in fact being reduced. At the same time, you can also see that the chlorine, having gone from -1 up to 0, is telling us that the chlorine is being oxidized. Remember that the oxidizing agent is that which has been reduced. So it actually aids the oxidation in happening, but it in and of itself is being reduced. And since it's an agent, do remember it needs to be a reactant, right? It needs to be the reactant that is in fact being reduced. So if we again look at our reaction here, you can clearly see that the chromium was being reduced. The chromium's reactant, so that which is on the left side of the arrow, is then the thing that is acting as the oxidizing agent. And of course, the reducing agent is the opposite. It's going to be that reactant which has been oxidized. And so again, if we look at our reaction, we see that the chloride ion was the reactant that hosted the chlorine atom in order for it to be oxidized, thereby making the chloride ion, Cl-, the reducing agent. All right, so that's a quick review. Let's also review going through balancing reactions. If you remember, there was a couple of videos that we made in Unit 3 for balancing reactions. One of those videos was by Mr. Seiler, and I believe that the other one was by myself. And I'm going to show you my method, but if you prefer Mr. Seiler's method, please go back into the Unit 3 videos and rewatch his for a refresher. Okay, mine's gotten started already because we already determined what the oxidation numbers are. So we're just going to go ahead and rewrite that just to make it clearer. Okay, so we've rewritten this reaction and clearly showing that the chromium in dichromate is positive 6, the chromium in chromium 3 is positive 3. That's our reduction. The chloride is negative 1, chlorine is 0. That's our oxidation. Keep in mind the very first thing that you always want to do is make sure that you've counted atoms. So up here, I'm going to go ahead and just write through the steps, right? So the first thing is count atoms. If you notice, we therefore have 2 chromiums on the left and only 1 chromium on the right. You want to make sure that you double that. If you double that, you're actually doubling the change in oxidation number as well. So let's go ahead and double those. Looking at the chlorine, same thing. There's 2 chlorines on the right and 2 chlorines need to be on the left. So again, we're going to fix those coefficients as well as double the oxidation numbers on each of them. That therefore means that we're going to see a positive 12 go down to a positive 6 for an overall change of 6 electrons. Now again, those 6 electrons are being reduced, they're actually being gained. And with the chlorine half reaction, we've got 2 electrons going from -2 to 0. Those electrons are being oxidized. So the second thing that you want to do is look at the number of electrons that have changed. All right, now that you've taken care of both of those things, we're going to go ahead and fix up some stuff. So the very first thing that we want to fix up is we want to make sure that the transfer of electrons from each of the half reactions is the same. A common multiplier would be great, so lowest common denominator is going to be a 6. The common multiplier then will give our 2 electrons multiplied by 3 to get to 6. That does mean you're going to bring that 3 into the coefficients of each one. So that's 1 times 3 for chlorine, 2 times 3 for chloride. So again, step 3, transfer the same number of electrons. That's also going to represent your N value, right? N is going to be the moles of electrons being passed, and that's going to be that quantity. So in this case, N is going to be 6. All right, next up, we're going to go ahead and just add water. We want to add water so that we balance off our oxygens. And since there are only oxygens over on the left-hand side, that makes it really nice and easy. We just need 7 oxygens, so we need 7 of the H2Os. Next, we're going to go ahead and we're going to add hydrogen ions. Again, since only hydrogens are on the right-hand side, you can see that there are 14 over here. That means that we're going to go ahead and add 14 H pluses on the left. We now have what should be a nice complete reaction. And the way to always check that reaction is to take and tally up all of your charges. So we've got a positive 14 coming from the 14 hydrogen ions. We've got a -2 coming from the dichromate. And then we've also got a -6 coming from the chloride. On the left-hand side then, that means that we have a total of positive 6. On the right-hand side, we're going to have 0 for the chlorine because they don't have a charge. We've got 2 of these positive 3 chromiums. That gives us a +6. And then water doesn't have a charge either, so our total charge on the right is positive 6. Since they're equal, we've got a perfect job making our reaction balanced. All right, let's do the same thing. This time, we're going to be working with a base, okay? Bases are just going to change the very, very last step. So again, I'm going to rewrite this and set up my oxidation numbers. Okay, so we have rewritten the reaction. In this case, for the cyanide versus cyanate, I'm going to go ahead and call the nitrogen a -3. If my nitrogen is a -3 in each case, remember that that means the -3 plus the carbon needs to add up to be a -1. That makes carbon plus 2. Over here, the nitrogen is -3, the oxygen is -2. That means that they together need to add up with carbon to make a -1. That's going to make carbon a +4. So going through the steps, we've got our oxidation numbers again. We're going to check that we have the same number of atoms. So carbon, there's 1 and 1, we're good. Nitrogen, 1 and 1, we're good. Manganese, 1 and 1, we're good. So double check that you've got your atoms counted up. We're now going to go ahead and calculate the difference in charge. So between 2 to 4, we are now losing 2 electrons. Right? Whoops, that's not an R, that should be an oxidation. Between 7 and 4, we are gaining 3 electrons. So that's going to be our reduction. Again, you want to get it so that the atoms are transferring the same number of electrons. That means that the common lowest number is going to be a 6. That means we're going to take our oxidation and multiply by 3, which will put a 3 in front of the cyanate and a 3 in front of cyanide. Similarly, we're going to go ahead and take our reduction 3 and multiply by 2. That'll put a 2 in front of manganese dioxide and a 2 in front of the permanganate. At that point, we can now start counting up oxygens. So again, you want to add waters. We've got 8 oxygens on the left, and 3 plus 4, 7 oxygens are on the right. So let's go ahead and add 1 more oxygen with 1 more water. You're then going to go ahead and add hydrogens. Now keep in mind, this reaction is you're being told needs to be balanced in base, but we're going to go ahead and add the hydrogens because it just makes life easy. Once you've got those hydrogens in there, let's go ahead and put in hydroxides. When you put in hydroxides, you're going to put them into both sides, just like in a math equation, right? So notice what I'm doing. I'm looking to put in the exact same number of hydroxides as hydrogens. If you're getting the gist from the acid-base chapter, that means these are going to react. They're going to turn into water. So we've now got 2 waters on the left. We still had the water from balancing the oxygen and 2 hydroxides on the right. Now we're going to simplify down. So that's the big difference. One more time. The big difference is because we're balancing in base, we're going to add hydroxides. How many hydroxides are we going to add? The same number as hydrogen ions that you just looked at. Where are you going to add them? Both sides of the reaction. Now once you've done all of that, we can go ahead and cancel some stuff out. That leaves us with just 1 water. And as we look at our final reaction, we'll have 1 water on the left, 3 cyanide ions, 2 permanganate ions, 3 cyanate ions on the right, 2 manganese dioxides, and finishing up 2 hydroxides. Again, if you just want to double check that you've done everything correctly, we're going to count up the charges. There's a 0 for water, a -3 for the 3 cyanides, a -2 for the permanganates, giving you a total of -5 on the left. 3 cyanates will be a -3 altogether, because again, you're multiplying. There's no charge on the manganese dioxide, but there are 2 hydroxides. Each one is -1, so -2. That's a -5 on this side. Yep, we did it. We end up having a nice balanced equation, balancing in base.